Welcome to the Architect of Sleep channel. Today we will embark on a journey to the cradle of light, into the silent nebulae, where stars are born from cold cosmic dust. We will witness the quietest and most grandiose miracle, the transformation of darkness into radiance. We will see how the invisible hand of gravity gathers scattered dust motes into a single whole, igniting a fire in their heart. This is a slow dance of creation, where eternity compresses into a single dazzling moment of a new sun's birth. This is the story of how emptiness learns to breathe light. If you enjoy these quiet journeys, I invite you to leave a like, subscribe, or share a thought below. This helps others find their way here, one sleepy soul after another. And now, simply breathe. Allow your eyes to grow heavy and your mind to soften. Let us begin. Far beyond our cozy world, in the velvety, inky void of interstellar space, float clouds so vast that it takes light entire centuries to cross them from edge to edge. These are not the fleeting clouds that race across Earth's sky, but colossal, primordial reservoirs of cold molecular gas, slumbering in eternal darkness. Their temperature is barely above absolute zero, by only a few degrees, where almost all atomic motion ceases. In their rarefied depths, a deep, pervasive peace reigns, incomprehensible to the restless human mind. But this silence is deceptive. It is filled not with emptiness, but with a quiet, dense promise, like a universe holding its breath. For it is here, in this cosmic twilight, like seeds in fertile, invisible soil, that all the future suns of the galaxy are stored. This is a cradle woven from darkness and cold, patiently waiting for its moment to awaken and shine. This promise is woven from the finest cosmic dust, hovering in the primordial mist, like a frozen echo of long-exploded stars. Each dust mote is a tiny refractory core of silicates, graphite, or even diamond, wrapped in the thinnest mantle of frozen water, methane, and ammonia. They are not mere cosmic debris, but the fundamental building blocks of the universe, its crystallized memory and its dormant potential. On their icy, porous surfaces, as if on microscopic altars, solitary atoms of hydrogen, the most abundant element in the universe, find each other and unite into molecules, releasing a grain of heat in the process. Thus the cloud grows denser, and each of these particles is a frozen thought of the cosmos, patiently awaiting warmth to tell its story of stardust and future fire. But how can we see these cold, dark clouds if they do not emit visible light, but only absorb it? We have learned to listen to their whisper, detecting the faint radio emissions that are sent out not by the main hydrogen molecules, but by their rare companions, such as carbon monoxide or CO. These indicator molecules, present in infinitesimally small quantities, colliding with each other in the cosmic cold, radiate at strictly defined frequencies, like tuning forks. By tuning our giant radio telescopes to them, we, like attentive listeners, can map these invisible giants, determining their density, temperature, and internal motion. We see the darkness not with our eyes, but with our ears, hearing the silent song of future creation, resonant and drawn out, like eternity itself. In this cold and rarefied space, a fragile, almost meditative equilibrium, like a dewdrop on the tip of a leaf, can reign for millions of years. On one hand, the barely perceptible thermal motion of gas particles, their own internal energy, compels them to move apart, gently pushing the cloud toward infinite expansion, toward dissolution in the void. On the other hand, the barely perceptible, yet omnipresent whisper of gravity forever tries to gather everything together, to pull the scattered into a whole, into a single dense heart. This is a long, almost eternal confrontation between two titanic yet unhurried forces, a sleepy balance that can only be disturbed by an external impulse or an internal disruption. The cloud waits, breathing on the scale of eternity until the invisible scales tip to one side, initiating an inexorable process. This balance is described by a simple yet profound concept, the Jeans mass, named after the astronomer who first conceptualized this cosmic Rubicon. For every region of gas with a specific temperature and density, there exists a critical mass, an invisible threshold. If the mass of the region is less than this limit, the internal pressure, like a resilient spring, will always prevail, and the cloud will expand or remain stable, continuing its sleepy drift. But if the mass exceeds the gene's limit, gravity becomes irresistible. Its quiet whisper turns into an insistent, commanding call, and this part of the cloud is doomed to collapse. It is an invisible line, crossing which signifies the beginning of the long and majestic journey from formless gas to a shining star. There is also a more general law of equilibrium, woven into the very fabric of the cosmos, that dictates the fate of every cloud. It is called the virial theorem. This fundamental principle links together two great forces: the internal energy of the particle's motion, their heat, which seeks to dissipate the cloud, and the gravitational energy, which seeks to compress it. The theorem states that for a cloud to be stable, its thermal energy must exactly balance half of its gravitational energy. This is the mathematical expression of that same fragile balance we have been discussing. As soon as gravity becomes too strong, for example, due to an increase in mass or a drop in temperature, this delicate equilibrium is broken. The theorem no longer holds, and the cloud begins its inexorable collapse into itself, obeying the voice of the strongest force in the universe. Sometimes this impulse pushing the cloud over the line comes from afar, like the thunderous echo of a long-past cosmic drama. The explosion of a supernova, located hundreds of light-years away, sends a shock wave of colossal power through space. This wave, like the invisible hand of a giant sower, shakes the sleeping molecular cloud, passing through it and compressing the gas in its separate, denser parts. It is like a cosmic embrace of death that bestows new life. Where the density suddenly increases, the gene's mass drops sharply, and gravity gains a new, decisive power. It no longer whispers, it begins to call, and the cloud, awakened from its long slumber, begins its slow and inexorable collapse, answering the call of a distant cataclysm. In other cases, the catalyst is not an explosion, but the majestic and unhurried dance of the galaxy itself, its own measured breath. The spiral arms that we see in its images are not just a beautiful pattern, but waves of increased matter density slowly rolling across the stellar disk like ripples on the surface of a cosmic pond. When a molecular cloud, on its long journey, enters such a shining whirlpool of creation, it falls into a zone of gravitational compression. Gas and dust are compressed, like water washing up on an invisible but insurmountable shore. Thus, the galaxy itself, with its unhurried rotation, helps its future children to be born, gathering them in its shining embrace and showing them a place for their birth. But birth does not always need such a dramatic push from the outside. The echo of an explosion or the touch of a galactic arm is not always required. Sometimes the process starts on its own, from within, in complete silence and tranquility. Inside a giant cloud, there is always turbulence, chaotic movements of gas similar to invisible currents in a deep ocean. These movements create random fluctuations in density. In some places, the gas becomes slightly denser, in others slightly more rarefied. And at times, by sheer chance, in one of these condensations, the mass of the substance exceeds the critical Jeans threshold. Gravity, in this small island of density, becomes the dominant force and triggers collapse. Thus, the universe demonstrates that it has many paths for the creation of light. Some are loud and explicit, others are born from quiet inner contemplation and chance. When gravity finally prevails, the giant cloud can no longer remain whole and monolithic. It is too large to collapse into a single point. It begins to break apart into numerous separate, denser fragments, each of which continues to contract independently, obeying its own center of gravity. This process, called gravitational fragmentation, is similar to how a large rain cloud breaks up into individual drops, each carrying a part of the whole but having its own destiny. Thus, a single immense cloud gives birth to an entire family of dense clumps, each holding the potential to become a star. This leads to the birth of star clusters, where hundreds of suns ignite almost simultaneously, like lights in a great celestial city. But for a cloud to break apart so elegantly, it must be not only heavy, but also sufficiently slow in its reaction. The fact is that any clump of density creates a pressure wave that propagates at the speed of sound, seeking to dissipate it. For a fragment to separate and begin its independent collapse, it must contract faster than this wave can cross it and smooth out the condensation. In cold molecular clouds, the speed of sound is extremely low, only a few hundred meters per second. This gives gravity a decisive advantage. The birth of a star cluster is a quiet, invisible race between gravity, which seeks to gather, and pressure, which seeks to disperse. A race measured by the speed of sound in near absolute cold. However, not every dense clump is fated to become a star. Some are merely elusive promises not destined to be fulfilled, silent dramas on a cosmic scale. Sometimes in the chaotic gravitational dance within a forming cluster, such an embryo, called a failed core, fails to gather sufficient mass. It can be torn apart by powerful tidal forces from more massive neighbors passing too close. Or a powerful stellar wind from hot stars already born nearby can simply blow away its material, like a hurricane blowing away a pile of dry leaves before the collapse becomes irreversible. It is the quiet story of a seed that fell on stony ground and could not sprout, dissolving back into the interstellar medium to one day become part of something else. Sometimes on the shining tapestry of the cosmos, the eye finds tears, coal-black spots like drops of spilled ink on stellar brocade. These are not holes in the fabric of being, but on the contrary, its densest and coldest knots, impenetrable cocoons of matter known as Bok globules. They are so dense that the light of myriad distant stars, having travelled for millions of years, becomes mired in them and fades, unable to break through. This creates the perfect illusion of an abyss, a silent window into nothingness. But within this velvety darkness, safely sheltered from the bustle and harsh radiation of the universe, slumbers the most concentrated promise of a future fire, one or several contracting embryos. Their darkness is not an absence, but an absolute presence, a curtain woven from cold and dust, behind which the greatest of miracles, the creation of light, is being prepared. And this miracle begins with a fall, the slowest and most majestic fall imaginable. In the heart of each such clump, each globule, matter rushes toward a common gravitational center, obeying an inexorable silent call. For tens and hundreds of thousands of years, this invisible collapse continues, this falling of gas into itself. As it compresses, the potential energy of the falling matter begins to convert into heat, following the fundamental laws of thermodynamics. The cloud, once one of the coldest places in the universe, begins to slowly but surely warm up from within, from its very contracting heart. This is the first timid, barely perceptible breath of the future fire, the first warmth born from cold and motion. But this fall is not straightforward, for the universe prefers not to fall, but to dance, obeying the ancient and immutable law of rotation. Any initial rotation, however slight, inherent in the original cloud due to turbulence or random movements, is amplified many times over as it contracts. This phenomenon, known as the conservation of angular momentum, is like an ice skater who, by pulling their arms in, begins to spin faster and faster. The slow and chaotic collapse transforms into an ordered and increasingly rapid vortex. Gravity gathers matter to a single point, while the law of conservation of momentum twists it into a giant cosmic spiral, preventing it from falling at once and creating a new complex structure. This accelerating rotation, like an invisible centrifugal force, prevents all the matter from falling directly into the forming center. Instead, it flattens the collapsing cloud along its axis of rotation, transforming the initially spherical clump into a flattened disc-like structure, similar to giant potter's clay in the hands of an unseen master. Thus, at the center of the giant vortex, a protostellar, or accretion disk, is born, a colossal carousel of gas and dust rotating around a central, even denser object. This disk is not only the building material for the future star, but also the cradle for its future planets, moons, and asteroids. The entire solar system is born from a single, graceful, and inexorable dance. In the earliest stages of this collapse, while the cloud is still sufficiently transparent, it contracts almost isothermally. This means that the heat generated by the compression is freely radiated into space, and the temperature of the clump barely rises, remaining at a level of a few tens of degrees above absolute zero. All the gravitational energy is converted not into heat, but into radiation, which is carried away by long infrared waves. This allows the collapse to proceed efficiently, without strong opposition from the internal pressure of the gas. The cloud falls into itself, remaining cold like a diver holding their breath before plunging into deep, dark waters, where transformation awaits. But as the core of the protostar becomes denser and hotter, it gradually becomes opaque to its own radiation, to the photons born from the compression. The moment comes when the collapse becomes adiabatic. Whereas in the earliest stages, heat freely escaped the rarefied clump, now the photons are trapped, constantly being absorbed and re-emitted by the particles of dense matter in an endless, chaotic dance. This leads to a sharp, avalanche-like jump in temperature and pressure at the very center. The protostar begins to lock heat within itself, accumulating energy for the decisive step in its evolution. It becomes like a sealed vessel in which an unthinkable, unimaginable pressure builds. At the very heart of this rotating disk, at the point of greatest density, a hot and dense ball of matter forms, the protostar. It is not yet a star in the full sense of the word, for there is no nuclear fire in its core, but it is no longer just a cloud of gas. It greedily absorbs matter from the surrounding disk, and this process, called accretion, causes it to grow in mass and heat up even more. Gas spirals down onto the surface of the protostar, adding mass and energy to it, like a river flowing into a growing lake. It already begins to glow, but not with the bright light of nuclear fusion, but only with the dim crimson heat of gravitational contraction, visible only in the infrared spectrum. This is the light not of burning, but of falling. In this incandescent, turbulent core, matter transitions into its fourth, most energetic state, plasma. At temperatures reaching millions of degrees, hydrogen and helium atoms lose their outer electrons, which can no longer be held in their orbits, transforming into an ionized, churning soup of free atomic nuclei and electrons. This is no longer a gas in the familiar sense, but a completely different, exotic medium with extreme density and energy, where particles collide with unimaginable force and speed. The space inside the protostar compresses to its limit, preparing for the final, great alchemical transformation that will turn simple matter into a source of light. At this stage, known as the T Tauri star stage, the protostar becomes extremely active, unstable, and even ferocious. It has not yet ignited its main nuclear engine, but it already exhibits a boisterous, unpredictable temperament, much like a restless adolescent. The most powerful stellar winds, supersonic streams of charged particles, erupt from its surface, hurtling into space at speeds of hundreds of kilometers per second. These winds collide with the surrounding disk and the remnants of the parent cloud, blowing away excess matter and gradually clearing the space around them. It is the furious cry of youth, asserting its right to a place in the universe, the first loud word in a long life. One of the most spectacular and grandiose phenomena of this turbulent era are the bipolar jets, cosmic lances of light and matter. From the poles of the rotating protostar along its axis of rotation erupt two narrow focused streams of superheated plasma. They pierce the surrounding cloud for light years, moving at speeds reaching hundreds of kilometers per second. Like a cosmic cannon, the twisted magnetic fields of the protostar and its disk gather, accelerate, and fire matter away from the system. These jets are the first loud exclamation of the newborn star, its majestic declaration of its right to exist, and a way to shed excess rotation. When these supersonic plasma jets slam into the colder, denser gas of the parent molecular cloud, they create powerful shock waves that cause this gas to glow brightly. These glowing knots, bizarre arcs and thin filaments are called Herbig-Haro objects. They are like cosmic neon signs, illuminating the invisible path that the stellar jets have forged through the darkness. By observing their shape and movement, astronomers can, as if following tracks in the snow, reconstruct the history of this turbulent birth period, seeing how the newborn star forcefully clears a living space for itself, drawing its first autographs in the cosmos. The pressure and temperature inside the protostar's core reach unimaginable, truly astronomical values, and gravity continues its relentless work, compressing it ever more tightly. With each new atom that falls onto it from the accretion disk, it becomes hotter, denser. Everything is ready for the final transformation, for the moment of truth, for the great culmination. The internal pressure of the hot gas is no longer able to resist the all-consuming gravitational compression on its own. The universe holds its breath in anticipation of the miracle that is about to occur in the very heart of this incandescent sphere. All the forces of nature have converged at a single point to give birth to a new reality. And then, the moment arrives when the temperature at the very core reaches a critical point, approximately 15 million degrees Celsius. At this temperature and monstrous pressure, the forces of electrostatic repulsion between the positively charged hydrogen nuclei, the protons, are finally overcome thanks to the purely quantum effect of tunneling. Protons begin to collide with such force that they fuse together in several stages, ultimately forming helium nuclei. This process, thermonuclear fusion, releases a colossal, almost unimaginable amount of energy according to Einstein's famous formula. In the heart of darkness, an unquenchable fire ignites. This is the birth of a star, the moment when gravitational contraction gives rise to a self-sustaining nuclear reaction that will burn for billions of years, converting mass into light. The energy released during the fusion process creates immense radiation pressure, directed outward from the core. This new powerful pressure begins to effectively counteract the force of gravity, which seeks to compress the star further. When these two great forces, gravity pulling inward and the nuclear fire pushing outward, balance each other, the star reaches a state of hydrostatic equilibrium. The collapse ceases, and the star achieves stability, beginning its long, steady life on the so-called main sequence. The first photons, born in the nuclear furnace at the very center of the star, begin their long and incredibly winding journey upward, to the surface. This path is anything but direct. A photon is constantly absorbed and immediately re-emitted in a random direction by particles of dense plasma, moving chaotically like a drunkard in a crowd, in an endless three-dimensional labyrinth. This journey from the core to the surface can take tens or even hundreds of thousands of years. The light we see from our sun today was born in its core, back when Neanderthals walked the earth. A star holds its light deep within itself for a long time before bestowing it upon the world, and every ray carries the memory of this long confinement. When this ancient light, reborn many times over, finally reaches the star's visible surface, its photosphere, it bursts out into open space and begins its straight-line journey across the universe at the speed of light. The protostar, which had glowed with the dim crimson light of contraction, transforms into a dazzlingly bright, fully fledged star, shining with its own nuclear fire. Its powerful light and intensified stellar wind begin to blow away the last remnants of gas and dust from the parent nebula. The cocoon that concealed its birth gradually dissipates, and the new star is revealed to the galaxy in all its splendor. The stellar nursery empties, releasing its shining charge into the vast and cold world. The mass a protostar manages to accumulate during its formation determines its entire future destiny, like a fate decreed at birth. If the clump of gas was too small, less than about 8% of our sun's mass, the temperature in its core will never reach the point required to ignite hydrogen fusion. Such an object will become a brown dwarf, a failed star, the eternal adolescent of the stellar world, one that never managed to light its own fire. It will only smoulder dimly in infrared light, slowly cooling in the cosmic silence for trillions of years, like an ember that never became a flame. If, however, the mass of a protostar is enormous, tens or even 100 times greater than the Sun's, its birth will be much more turbulent, swift, and violent. Gravitational collapse occurs incredibly fast, and the temperature and pressure in the core increase like an avalanche. Such a star ignites in just a few tens of thousands of years, and immediately begins to shine with unimaginable power, like a cosmic diamond visible from the other end of the galaxy. But its life will be short and brilliant. It will quickly burn through its fuel and end its journey in a dazzling supernova explosion, illuminating the galaxy with a final flash and enriching it with heavy elements for future generations. But for a star like our Sun, a long and surprisingly stable period begins, known as the main sequence. For billions of years, it will methodically and steadily convert hydrogen into helium in its core, maintaining an ideal, almost perfect balance between the force of gravity and radiation pressure. This is the calmest time in a star's life, its maturity and prime, its long, peaceful summer. It becomes a reliable source of light and heat, creating around itself a so-called habitable zone, where, on planets fortunate enough to be there, liquid water and possibly life can exist. It becomes the center and guardian of its own small world. The silence of the primordial nebula is broken not only by the birth of stars, but also by their subsequent gravitational dance. In dense stellar nurseries, where stars are born close to one another, young stars can strongly influence each other. Some of them are captured by a neighbor's gravity and form binary, or even multiple systems, beginning an eternal waltz around a common center of mass. Others, as a result of a too close encounter, can be ejected from their native cluster, like balls in a game of gravitational billiards, and sent on a solitary journey through the galaxy. The cradle can be not only cozy, but also cruel, separating its children and determining their fates by a chance encounter. The very first stars in the universe, the so-called population 3 stars, were true cosmic pioneers, giants of legend. They formed from clouds consisting almost entirely of hydrogen and helium, the lightest elements born in the fire of the Big Bang itself. They lacked the dust and heavy elements that help modern clouds to cool effectively. Therefore, the first stars were, as models predict, incredibly massive, hundreds of times more massive than the Sun, and lived for a very short time, only a few million years. But it was they that, upon exploding, created the first heavy elements, carbon, oxygen, iron, and seeded the young universe with them, making the birth of second-generation stars possible. Modern stars, like our Sun, belong to population 1, and they are born in clouds already generously enriched with heavy elements, everything heavier than hydrogen and helium, which astronomers call metals for short. These metals, such as carbon, oxygen, silicon, and iron, make up the very dust particles that are so important for the process of star formation. They act as effective coolants, allowing the gas to compress more tightly and form lower-mass stars capable of living long and stable lives. We are the children of second- and third-generation stars, born from the reprocessed ashes of long-extinguished suns, and we carry their legacy in every cell of our bodies. The presence of these metals in the cloud drastically changes its ability to cool. While hydrogen molecules radiate heat rather reluctantly, the atoms and ions of heavy elements, such as carbon and oxygen, do so much more effectively. Colliding with gas particles, they become excited, and then almost instantly shed this energy by emitting a photon in the infrared range, which easily escapes the cloud. They act like tiny but extremely efficient radiators, like open vents in a heating room, allowing the cloud to remain cool even as it contracts. It is this cooling ability that allows the cloud to fragment into smaller pieces and give birth to stars the size of our sun, and not just giants. Magnetic fields, permeating the molecular cloud with their invisible lines of force, play the role of a hidden yet powerful conductor in this cosmic orchestra. In the initial stages, they can support the cloud, preventing it from collapsing under its own gravity, acting as a kind of resilient magnetic spring that resists compression. But they can also direct the flow of gas falling onto the protostar, shaping the structure of the accretion disk and helping to launch those very bipolar jets. Magnetism is the invisible force that gives the process of star birth its complex, orderly, and mesmerizing beauty, turning a simple fall into an intricate dance. This process of resisting collapse is called ambipolar diffusion. It is a slow, almost meditative dance of matter and field. The magnetic field is frozen only into the charged particles, ions and electrons, which are very few in the cold cloud. The vast mass of neutral gas molecules does not feel the field directly and, under the influence of gravity, slowly percolates through it like water through sand. This slow drift allows the matter in the center of the clump to gradually condense until its gravity becomes strong enough to drag the magnetic field along with it. It is a quiet, centuries-long struggle in which gravity ultimately wins, thanks to its infinite patience and persistence. The rotating disk around a young star is not just mechanical motion, but a living, breathing, and complex organism. Friction between adjacent layers of gas, moving at slightly different speeds, generates turbulence and so-called viscosity. This viscosity causes the gas to slowly lose its orbital energy and spiral gently down towards the protostar, providing it with continuous nourishment for hundreds of thousands of years. The disk is not a static structure, but a complex hydrodynamic system that feeds its infant and simultaneously shapes its future planetary environment, being both a dining hall and a cradle. In the colder outer parts of this giant disk, beyond the so-called snow line, the temperature drops so low that volatile compounds like water vapor can condense into tiny ice crystals. Here, dust grains coated in sparkling frost become stickier and begin to effectively clump together upon collision, forming progressively larger bodies. This is how planetesimals are born, the kilometer-sized seeds of future planets. The process of planetary system formation occurs simultaneously with the final stages of the star's birth, like a single act of creation from the same rotating cloud of matter, like two voices in one song. However, the birth of giant planets, such as Jupiter, presents a puzzle for which there are two main explanations. According to the core accretion model, a solid core of rock and ice, 5 to 10 times the mass of Earth, forms first. When it becomes massive enough, its gravity begins to rapidly attract huge volumes of gas from the surrounding disk. The alternative model, the gravitational instability model, suggests that dense spiral arms can arise in massive and cold disks, which quickly collapse under their own gravity, forming a giant planet entirely in just a few thousand years. Perhaps the universe uses both of these pathways to create its largest and most majestic worlds. Studying these processes is like cosmic archaeology, as we cannot observe the birth of a single star from beginning to end. This process is too long for a human lifetime. Instead, astronomers find thousands of stellar nurseries in our galaxy at various stages of evolution, from cold, dark clouds to young star clusters, shining with the light of newborn suns. By assembling these snapshots into a single logical sequence, they reconstruct the complete picture of this majestic process, as if piecing together a person's life story from scattered photographs in the universe's vast family album. Telescopes operating in the infrared and radio wavelengths have become our main guides on this journey into the past, our eyes capable of seeing the invisible. Ordinary visible light cannot penetrate the dense, dusty cocoons surrounding protostars. It is absorbed and scattered by them. But the long waves of infrared radiation and radio waves pass through the dust, like light through a light morning fog, allowing us to peer inside the dark globules and see the heat emanating from nascent stars and their disks. We have learned to see in the dark, and it has revealed to us its most intimate secrets of creation, its quiet, warming light. The light of a newborn star, when it finally breaks through, carries a secret message about its composition and origin. By analyzing the spectrum of this light, breaking it down into a rainbow with prisms and diffraction gratings, scientists can see the dark absorption lines corresponding to specific chemical elements in its atmosphere. This allows them to determine precisely which elements are present in the star and in what proportions, and to understand what material the original cloud was made of and to which generation of stars it belongs. Every ray of light is a letter from the past, telling the story of its origin and its long journey to us. The powerful ultraviolet radiation of a young, hot star is not only light, but also a force capable of creating and destroying. In just a few million years, it can completely ionize and evaporate the surrounding protoplanetary disk, blowing the gas into interstellar space. This creates a kind of temporal window for planet formation. Giant planets, which need gas to grow, must manage to grow before their main building material is irreversibly blown away. It is a cosmic race against time, in which only the fastest and luckiest worlds survive and form, having managed to gain mass before their cradle evaporates. The remnants of a molecular cloud, scattered and illuminated by the light of young stars, often create incredibly beautiful and breathtaking spectacles. Emission nebulae. Harsh ultraviolet radiation from hot stars strips electrons from the atoms of surrounding hydrogen, ionizing it. When these electrons recombine with nuclei, they emit light at specific wavelengths, causing the gas to glow with a characteristic crimson-red color, the color of life and energy. The Orion Nebula, or the Carina Nebula, are giant canvases painted by the light of newborn suns on the canvas of the cosmos, their first collective work of art. Sometimes not one, but two protostars form within a protoplanetary disk, orbiting a common center of mass. If they are close enough, they can form a close binary system, beginning their gravitational dance from the very moment of their birth. In such systems, the stars can exchange matter through their accretion disks. or via stellar wind, and their evolution will differ greatly from that of single stars. Their lives and fates are intertwined from the very beginning, creating complex and sometimes dramatic cosmic scenarios unavailable to single stars, and making their shared existence richer and more complex. The rate of a cloud's collapse depends directly on its initial temperature, on how cold it is. The colder the gas, the lower its internal thermal pressure, which resists compression, and the easier it is for gravity to begin its work and initiate the process. This is precisely why cosmic dust is so important. Its icy surface helps molecules to form, and the dust grains themselves efficiently radiate heat in the infrared range, cooling the cloud like tiny radiators. Without these tiny icy particles, star formation would be a much less efficient process. Cold is not an enemy of life, but its distant, silent, and indispensable progenitor. The very act of observing starbirth changes our fundamental understanding of the universe. We see that the cosmos is not a static, frozen void, but a dynamic, ever-changing, and evolving environment, a living organism. It is a place where creation is constantly occurring on the most grandiose, unimaginable scales. The birth and death of stars is the great engine of cosmic evolution, a process that creates the heavy chemical elements from which, ultimately, we ourselves and everything around us are made. We are children of the stars, in the most literal sense of the phrase, created from the ashes of long-extinguished suns and holding their light within us. As a protostar contracts, its initial weak magnetic field intensifies along with it, concentrating at the center like rubber bands. The magnetic field lines passing through the accretion disk inevitably get twisted due to the difference in rotational speeds at various distances from the center, like a coiling telephone cord. This twisting, similar to winding a rope, creates colossal magnetic tension. Seeking to straighten out, this tension can eject matter in the form of powerful jets along the axis of rotation. The magnetic field acts as a mediator, transferring energy and angular momentum from the star to the disk and back, conducting this complex exchange. Sound, as we know it, cannot travel in the vacuum of space. It needs a medium. But if we could hear the processes inside a molecular cloud, it would be a majestic symphony of ultra-low frequencies, the true music of the spheres. We would hear the deep, bass-like hum of gravitational contraction, building over millennia. To this would be added the sharp whistle of shockwaves from supernova explosions and the quiet crackle of magnetic reconnections in the disk. This is the music of creation, performed on scales inaccessible to human hearing, but perceptible through the sensitive language of mathematics and physics. A silent song of the birth of worlds. In the dense, hot cores of protostars, even before the main hydrogen fusion begins, other, less energy-intensive nuclear reactions can occur. For example, fusion involving deuterium, a heavy isotope of hydrogen, which begins at a lower temperature, around 1 million degrees. This reaction serves as a kind of fuse or match for the main thermonuclear fire. It cannot stop the star's contraction, but it releases enough energy to slow it down and help the core heat up to the 15 million degrees necessary to ignite the true, long-lasting stellar fire. It is the first spark heralding the great flame. The rotating disk around a young star is not only the birthplace of planets, but also a highly complex chemical factory operating on a cosmic scale. under the influence of harsh ultraviolet and X-ray radiation from the young star and cosmic rays, complex organic molecules, alcohols, sugars, and even amino acids, the building blocks of life, are formed in the disk. These molecules can then be delivered to young planets by comets and asteroids that bombard their surfaces, seeding these new worlds with the potential for future biological evolution. The cradle of stars can also be the cradle of life, preparing its ingredients long before suitable conditions arise. Directly around the protostar itself, in the innermost and hottest part of the disk, there is a region that astronomers call a hot core, or carino. Here, at temperatures of hundreds of degrees, complex molecules evaporate from the icy mantles of dust grains, creating an incredibly rich chemical brew. It is a true cauldron where even more complex organic compounds are born. By studying the spectrum of these regions with radio telescopes, we are, as it were, reading a cookbook of prebiotic chemistry, seeing how the cosmos creates the ingredients for life even before the planets themselves have formed. It is a chemical dawn preceding the biological one. When a star finally stabilizes on the main sequence, its luminosity and temperature remain almost unchanged for billions of years. This predictability and reliability are a key factor for the development and sustenance of complex life as we know it. It provides a constant and steady flow of energy, necessary to maintain liquid water and complex biochemical processes on the surface of planets in the habitable zone. The star becomes a reliable guardian for its child worlds, warming them with its steady, unfading light throughout geological epochs, like an eternal, caring parent. Sometimes a giant molecular cloud fragments into such small but numerous pieces that entire swarms of red dwarfs are born from them. These are the smallest, dimmest, and most numerous stars in the universe, making up to 3/4 of the entire stellar population of the galaxy. They burn their hydrogen fuel very economically and slowly, and their lifespan can be trillions of years, far exceeding the current age of the universe. They are the quiet, almost eternal witnesses of all cosmic history. Silent long-livers who will see the distant future of the cosmos when all brighter stars have long since faded. While observing young stars, astronomers encountered a puzzle known as the protostar luminosity problem. Simple models predicted that the process of constant smooth accretion should make protostars much brighter than they are actually observed to be. It seemed that the stars were under-eating, or that we were missing something in our understanding of their growth. This puzzle forced scientists to reconsider their views on how exactly a star gains mass, leading to the realization that this process is far from as smooth as previously thought. The mystery of the protostar's dimness held the key to their turbulent and intermittent youth. The process of matter falling onto a protostar from the disk is not always smooth, gradual, and uniform, and herein lies the solution to the luminosity problem. Sometimes, due to gravitational instabilities, a large amount of matter accumulates in the disk, which then collapses onto the star in a sudden, powerful avalanche. This leads to a sharp and dramatic increase in its brightness, as if it momentarily flares up. Such outbursts, like those of Fu Orionis-type stars, can increase luminosity by hundreds of times in just a few months. These are the growth spurts of a stellar infant, its greedy, intermittent inhalations of matter, alternating with long periods of calm. The shape of the nebula from which stars are born is often complex, filamentary, and fractal, resembling a cosmic web or a neural network. These filaments are the densest parts of the cloud, where star formation is most active. Stars are not born uniformly throughout the volume, but along these elongated threads like pearls on an invisible string, especially at their intersections in the densest nodes. Gravity prefers to gather matter along existing paths of least resistance, following invisible rivers of increased density carved by turbulence and magnetic fields. When the most massive and hottest stars ignite within a cloud, their powerful ultraviolet radiation ionizes the gas, but it can also halt the birth of other less massive stars nearby. This phenomenon is called negative feedback. The radiation and stellar winds heat and disperse the surrounding gas, increasing its internal pressure and preventing it from collapsing under gravity. Thus, the largest and brightest stars can sterilize their surroundings, preventing their younger, less massive siblings from being born and ultimately destroying the very cradle from which they themselves just emerged. In the most extreme conditions, for example, in the centers of galaxies where the gas density is enormous, or during the collision of two galaxies, true bursts of star formation, or starbursts, can occur. Hundreds of thousands or even millions of stars are born in a relatively small volume over a geologically short period of time, in just a few tens of millions of years. Such regions glow with incredible brightness, sometimes outshining the light of the entire rest of the galaxy. These are cosmic fireworks that mark turbulent, pivotal epochs in the life of the universe, periods of great and furious creation. As a protostar gains mass and evolves, its internal structure changes, adapting to new conditions. In the earliest stages, on the Hayashi track, it is fully convective. The matter within it is constantly mixing, like in a boiling cauldron, efficiently transferring heat from the hot center to the outside. Later, when nuclear fusion ignites and the temperature in the core rises, a radiative core forms in a star like the Sun, where energy is transferred by photons and only an outer convective envelope remains. Its internal architecture becomes more complex, adapting to the new, much more powerful energy source. Ultimately, everything we see around us, from the stone under our feet and the iron in our blood to the air we breathe, was once part of such a cold molecular cloud. The elements created in the hearts of long-dead first and second generation stars were scattered into space by supernova explosions, then gathered into a new cloud from which the Sun and our Earth were born. The story of a star's birth is also our own, deeply personal origin story, written in the language of cosmic dust and starlight, and we are its living, breathing continuation. Gravity, initiating this long and complex process, acts as a great, yet invisible and infinitely patient sculptor. It takes a formless, chaotic, cold cloud and gives it a clear, ordered structure. A spherical core, a flattened rotating disk, elongated collimated jets. It transforms chaos into cosmos, disorder into order. The birth of a star is a local but grand triumph of order and structure over the universal tendency towards decay and entropy. A triumph of creation, albeit temporary on the scale of eternity, but no less beautiful for it. Even after the star has ignited and reached the main sequence, accretion from the disk can continue for some time, though on a much smaller, diminishing scale. This residual, thin flow of matter, like a quiet stream, influences the star's early evolution, its rotation speed, and the chemical composition of its atmosphere. The star and its protoplanetary disk remain connected for a long time after its official birth, like a child and mother, bound by the invisible thread of a common origin and a long exchange of matter, until the stellar wind finally severs this connection. The light from the most distant, and therefore most ancient newborn stars, which we are just beginning to capture with the James Webb Space Telescope, is light from a time when the universe was only a few 100 million years old. By studying it, we are peering into the very beginning of the Age of Light, into the cosmic dawn, when the first suns, the population 3 stars, pierced the primordial darkness left after the Big Bang with their radiance. They began to fill the young cosmos with heat, light, and heavy elements, initiating the great cycle of cosmic evolution that continues to this day. The rotational speed of a young star gradually but steadily slows down over time. Its powerful magnetic field, interacting with the streams of charged particles of the stellar wind, creates a kind of magnetic break. The field latches onto the escaping matter and transfers part of its angular momentum to it, effectively carrying it away into space. Young stars rotate very quickly, completing a rotation in a few days, whereas our adult sun completes a rotation in about 27 Earth days. With age, stars become slower, more sedate, and calmer, losing the fervor of their turbulent youth. Turbulence in a molecular cloud plays a dual, almost paradoxical role. On one hand, it can create local clumps of density that then collapse into stars, initiating the process of star formation, as if stirring a soup and creating lumps in it. On the other hand, it can also support the cloud as a whole, creating additional effective pressure and hindering general gravitational collapse. It is a complex non-linear dance where creative and destructive forces are in a constant, inseparable, and delicate dialogue, determining the overall efficiency of starbirth in the galaxy. When a bipolar jet breaks through its parent cloud, it creates a long and narrow tunnel within it, a cavity cleared of gas and dust. When the star finally clears its immediate surroundings, its light begins to pour through these tunnels, like a searchlight beam, and reflect off their walls as if in a cave. This is how bipolar reflection nebulae are formed. 2 beautiful cones of light diverging from the invisible star at the center. It is like a beacon lit in a dense fog, whose light indicates the birthplace of a new star and traces its axis of rotation in the sky. The entire combination of these processes, from a cold, rarefied cloud to a radiant star and its forming planetary system, takes from several to tens of millions of years. For us, with our short lives, this is almost an eternity. But on the scale of a galaxy's life, which spans billions of years, it is but a single, fleeting moment. The universe is in a constant process of self-renewal, and the stellar nurseries scattered across its expanses are its ever-working maternity wards, where darkness is continuously and relentlessly transformed into light, where emptiness finds a voice and warmth. By studying meteorites that have fallen to Earth, especially the most primitive ones as chondrites, scientists find microscopic presolar grains in their matrix. These are the very refractory dust particles of silicates, graphite and silicon carbide that existed in our parent molecular cloud, even before the birth of the Sun. They survived the formation of the solar system, were incorporated into asteroids, and have brought us news of the chemical and isotopic composition of that ancient nebula. They are true time capsules, material messengers from an era that preceded our birth, the most ancient relics of our world. Imagine you are standing on the surface of a young, still-forming planet in such a system. The sky above you is not yet black, but filled with glowing, shimmering wisps of the parent nebula, illuminated from within by the light of thousands of stars. Nearby, just a few light-years away, hundreds of young hot sister stars shine, close and dazzlingly bright, like diamonds on velvet. Night, as we understand it, does not yet exist. It is a world of perpetual, fantastical twilight and cosmic fireworks. A world we will never see, but can recreate in our imagination by listening to the quiet whisper of the stars and their distant stories. The final mass of a star is perhaps the most important, fundamental parameter that determines its entire future life and death. It determines its luminosity, surface temperature, color, lifespan, and how it will die, quietly fading as a white dwarf or exploding as a supernova. Everything is decided at the very beginning, in the process of accretion, in that silent struggle between gravity, pressure, and centrifugal force that occurs in the depths of a dark stellar cradle. A star's fate is written even before its birth, and it is impossible to change this record. This fate, the distribution of stars by mass, follows a statistical law known as the initial mass function. This law states that for every one massive star, tens of medium-mass stars and hundreds of low-mass dwarfs are born. The universe prefers to create long-lived but dim laborers, rather than bright but short-lived giants, like a wise gardener planting more slow-growing oaks than fast-burning flowers. This law, derived from observations, is one of the cornerstones of modern astrophysics, determining the evolution of light and matter in galaxies as a whole. The process of cloud fragmentation does not always lead to the birth of separate, independent stars. Sometimes two dense clumps are too close to each other, and continuing to contract, merge into one more massive object, uniting their destinies. Or, conversely, one large, rapidly rotating clump may not withstand the centrifugal forces and split in two during the collapse, giving birth to a close binary system. The dynamics of this process are chaotic and unpredictable in detail, but always obey the general immutable laws of physics and gravity, creating an infinite variety of stellar families. In the heart of a protostar, even before hydrogen ignition, a constant tuning of its structure takes place. The object slowly contracts, its surface heats up, then cools down, its density increases, and it seeks its equilibrium. Astronomers track this period, which precedes the main sequence, along the so-called Hayashi track on the temperature-luminosity diagram. The protostar slowly moves down this path toward its final stable state, as if searching for its one destined place in the universe, its note in the great symphony of the cosmos. After the Hayashi track, when the protostar becomes hot enough and a radiative core forms in its interior, it transitions to the Henye track. Now it continues to contract, but its luminosity hardly decreases, while its surface temperature, on the contrary, increases. It moves almost horizontally to the left on the diagram, toward the main sequence. This is the final stage of its journey to maturity, the final push before the beginning of a long and stable life, the last effort before taking its place in the stellar ranks. Each type of star follows its own unique path on this map of stellar destinies, and this path is predetermined by its mass. Sometimes young stars are surrounded not only by a disk, but also by a residual, dense spherical envelope of gas and dust, which is still falling onto the system from all sides. This is the earliest stage, the so-called Class 0 object. It is practically invisible, even in the infrared range, and reveals itself only through weak millimeter radiation from cold dust and powerful bipolar jets breaking through the cocoon. This is a stellar embryo in the deepest and most hidden stage of its development, wrapped in a dense blanket of matter, invisible to the world but already announcing itself with its hidden power. Over time, the star and its birth siblings migrate through the galaxy, moving away from their birthplace and from each other under the influence of the galaxy's gravitational fields. After hundreds of millions of years, the stars from one cluster are scattered throughout the galactic disk, and their paths diverge forever. But their chemical composition, their DNA, forever remains common, like a genetic marker. This allows astroarchaeologists using so-called chemical tagging to find long-lost relatives and reconstruct the history of their common family, their shared origin from a single ancient cloud. Open star clusters, such as the famous Pleiades, are beautiful examples of young stars that have not yet had time to drift far apart. We see them surrounded by a gentle, bluish haze. These are the last remnants of the parent nebula, whose dust reflects and scatters the light of the hot blue stars. It is a beautiful snapshot of stellar youth, frozen in time for our contemplation. A quiet reminder that all stars, even the most solitary ones, were once part of one large and close-knit family, born in the same cradle. In contrast, globular clusters are ancient, almost mythical relics of the early universe. They contain hundreds of thousands or millions of old stars, gravitationally bound into a dense, shining sphere. They were born under very different conditions, in gigantic starbursts when the galaxy was young. These clusters are not just families, but entire city-states that have survived billions of years of cosmic history. They orbit our galaxy like grey-haired sages, holding the memory of times we will never see, and of entirely different ways of giving birth to light. The birth of a star is not just a physical process, but a profound, fundamental act of transformation. The invisible becomes visible. The cold becomes unbearably hot. Chaos transforms into order. The potential energy of gravity converts into the kinetic energy of motion, then into thermal energy, and finally into the dazzling, life-giving energy of light. This is the fundamental chain of transformations underlying all activity and complexity in the universe, the great alchemy of the cosmos, turning simple hydrogen into radiance and ultimately into life itself. The process of accreting matter from the disk onto the star is not 100% efficient. A significant portion of the matter approaching the star does not fall onto it, but is caught by powerful magnetic fields and ejected back into space in the form of the same jets or wide disk winds. The star, therefore, not only absorbs but also gives back, actively regulating its own growth and shaping its immediate surroundings, like a sculptor who not only adds clay but also carves away the excess. This is a complex feedback system where the object of creation itself becomes the creator of its environment. In the densest regions of young star clusters, protostars can be so close to each other that their accretion disks interact, are distorted by the gravity of their neighbors, and can even be torn away. Close flybys of other stars can strip the outer parts of the disk where planets form, leaving the star without its retinue, or with a severely truncated planetary system. The fate of a planetary system depends not only on the star itself, but also on how turbulent its childhood was in the stellar nursery, on chance encounters and gravitational upheavals. Even after thermonuclear reactions have begun in its core, a star does not immediately become visible in the optical range to an observer. It needs time for its powerful wind and radiation to burn a window through the surrounding dust cocoon. This moment, when the star first becomes visible to the naked eye or an optical telescope, is what astronomers call the birth line on the evolutionary diagram. It crosses this line to officially join the visible population of the galaxy, announcing itself to the world with its own undistorted light, like a newborn opening its eyes for the first time. When we look at the famous Pillars of Creation nebula in the constellation Aquila, we are seeing this very process in action, frozen in eternity due to the finite speed of light. The giant columns of cold gas and dust are remnants of a molecular cloud that have not yet been destroyed and evaporated by the powerful radiation of young, hot stars born nearby. At the tips of these cosmic fingers, gravity is right now forming new protostars hidden inside dense gas clumps. We see both creation and destruction in one grand frame, the eternal drama of birth and death played out on the celestial stage. Surprisingly, even supermassive black holes at the centers of galaxies can influence starbirth on a galactic scale. Powerful jets and winds emitted by an active black hole can, on one hand, compress interstellar gas and trigger a wave of star formation, acting as a giant trigger. On the other hand, they can heat and accelerate it so much that they completely halt the birth of new stars in the galaxy for billions of years, making it red and dead. Everything in the universe is connected in a single, complex and not always obvious dance, where the center and the periphery are in constant dialogue. Cosmic dust, which seems so insignificant, is actually one of the key and indispensable players in this drama. It not only helps to cool the gas and serves as a nucleus for the condensation of hydrogen molecules, but also protects the inner dense parts of the cloud from the destructive ultraviolet radiation of other stars. Without this dusty veil, the complex molecules necessary for cooling would be destroyed, and the gas would not be able to cool enough to collapse. Darkness protects the light before allowing it to be born, and dust is the matter of this protecting darkness, this cosmic curtain. The rotation of a protostar and its disk almost always occurs in the same direction. This is a direct legacy of the very same initial, barely perceptible rotation of the parent cloud, amplified many times over by the law of conservation of angular momentum. This is precisely why in our solar system, all planets orbit the Sun in roughly the same plane, the ecliptic, and in the same direction. It is a shared deep memory of our birth from a single giant cosmic vortex billions of years ago, imprinted in the architecture of our home. Stars are not born in an absolute void. The interstellar medium is permeated by cosmic rays, high-energy particles, mostly protons, flying from supernova explosions and other active objects. These rays constantly bombard molecular clouds, ionizing the gas in their depths, influencing its chemistry, creating ions that cling to the magnetic field and serving as an additional source of heat. They are another subtle, yet important factor that must be considered in the complex model of star formation, another invisible thread in the great tapestry of creation. light from a newborn star, traveling through the remnants of its surrounding nebula, is scattered by microscopic dust particles. Short wavelengths, corresponding to blue and cyan light, scatter much more strongly than long wavelengths, corresponding to red. Therefore, if we look at a star through a dense cloud, it appears redder to us than it actually is. This phenomenon is called interstellar reddening, and the dust itself, illuminated from the side, appears blue to us, creating a reflection nebula. Thus is born the rich and delicate palette of cosmic landscapes, a play of light and shadow, of blue and red. In the densest and most active regions of star formation, a unique phenomenon can be observed: matter emission. Molecules of water, hydroxyl or methanol, excited by radiation from protostars, begin to act as natural microwave lasers, or masers. They emit incredibly powerful and narrowly focused beams of radio waves. To radio telescopes, these masers flare up like the brightest beacons, allowing for incredibly precise measurements of gas motion and magnetic fields in the very hearts of stellar nurseries, where no other instrument can peer, giving us a map of the most intimate processes. This entire grand multi-layered picture, from a dust particle to a star, from a cold cloud to a planetary system, obeys the same fundamental laws of physics that we study here on Earth: gravity, thermodynamics, electromagnetism, quantum mechanics. The universe is unified and consistent in its manifestations, and by studying the birth of a distant star, we gain a deeper understanding of the world we live in and of ourselves in. The cosmos is not some alien and distant place. It is our greater home, built according to unified and beautiful rules that connect the atom and the galaxy. Young stars often exhibit powerful X-ray flares associated with the fierce activity of their magnetic fields, which are much stronger and more tangled than those of our mature sun. Giant coronal mass ejections and violent flares on their surface, thousands of times more powerful than solar ones, are common for these troubled teenagers of the stellar world. A young planetary system must withstand this storm in the first millions of years of its existence, being tempered in the fire and wind of its newborn star, and forming its atmosphere under this harsh influence. When a star, with its light and wind, burns and disperses its dust cocoon, it does not just reveal itself to the world. It actively changes the chemistry of the surrounding interstellar space. Its harsh ultraviolet radiation creates so-called photodissociation regions at the boundary with the cold cloud, where molecules break down into atoms and the gas heats up and glows in unique spectral lines. The star becomes the center of its own small ecosystem, influencing everything around it and creating unique conditions in its corner of the galaxy, reshaping it in its own image and likeness. The process of star formation on a galactic scale is self-regulating. The birth of massive stars leads to the destruction of the parent cloud, which halts further star birth in that region. But the matter scattered into space by supernova explosions and stellar winds will one day cool, become enriched with new elements, and gather again in another place to give rise to a new generation of stars. This is an eternal cycle, the great pulsation of the galaxy's life, where calm is replaced by activity, and the death of one generation gives rise to another, like the cycle of seasons on Earth. Peering into the depths of nebulae with the most powerful telescopes, we do not see the past in a frozen, museum-like state. We see the present, happening right now. but tens, hundreds, or thousands of light years away from us. The light from these events takes so long to reach us that we see them with a huge delay. But somewhere out there, at this very moment, as you listen to these words, gravity is compressing another cloud, and in its heart, a new yet unseen fire is about to ignite. The universe lives and breathes not in the past but right now, and we are merely distant witnesses to its eternal present. Every star is a silent story of great overcoming. Overcoming the thermal pressure that seeks to tear the cloud apart. Overcoming the centrifugal force that prevents matter from falling to the center. Overcoming the magnetic resistance that keeps the gas from compressing. Gravity is a slow but inexorable and most patient force of the universe, which in the end almost always wins, step by step, drawing matter toward a single goal. The birth of a star is not an explosion, but a slow, persistent compression that in its culmination gives birth to light. It is a quiet victory, the echo of which reverberates for light years around. Whenever you feel the warmth of sunlight on your skin, pause for one brief moment. This light, these photons, were born in the thermonuclear heart of our star, which in turn was ignited by the slow and inexorable gravitational collapse of a giant cloud of cold gas and dust over 4.5 billion years ago. You are feeling the final echo of the very creation of our world, the culmination of a long journey from darkness to light, from cold to warmth, which has ended here, now, on the palm of your hand. You are touching a story told by light. Ultimately, every point of light twinkling in the night sky is a story of immense success. A story of how, from chaos, cold, and darkness, thanks to the persistent and quiet call of gravity, an ordered, hot, and stable structure was born, bestowing light and warmth. It is a quiet yet tangible reminder that even in the deepest darkness and apparent emptiness, an unimaginable, infinite potential for radiance is hidden. It only takes time, patience, and the right conditions for it to manifest and illuminate the world around with its quiet, steady light. Thus, from silence and cold, the music of light is born. We have traveled the path from scattered dust to a shining sun, from a dark cradle to a bright star. We have seen how the invisible force of gravity weaves the fabric of being, transforming chaos into harmony and emptiness into a source of life. Every star in the night sky is not just a point, but a completed poem of transformation. If you enjoy these quiet journeys, I invite you to leave a like, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. And now, just breathe. Let your eyes grow heavy, and let the quiet newborn stars lull your thoughts. Good night.